we get U1 plus P1 V1 plus V1 square by 2 plus G into Z1. These are all the energies that are entering with the mass into the control volume at section 1 plus heat supplied to the control volume is equal to m dot 2 into U2 plus P2 V2 flow work, that is, plus kinetic energy V2 square by 2 plus potential energy Z into Z2 plus W shaft. The sum of all these energies is the energies leaving the control volume at section 2. For steady flow conditions, the rate of energies entering the control volume must be equal to the rate of energies leaving the control volume. This is energy balance equation. Now let us put m dot 1 is equal to m dot 2 is equal to 1 kg per second. That we assume that mass flow rate is unity at inlet and at outlet. Then heat supplied to control volume per unit mass, that is capital Q divided by mass, is equal to small q joule per kg. Small q is the rate of heat energy supplied per unit mass of the control volume. Similarly, work done by unit mass of fluid flowing through the control volume is equal to capital W SH divided by M, that is small w joule per kg, where small w is the shaft work done per unit mass flow rate of fluid passing through the control volume. That implies U1 plus P1 V1 plus V1 square by 2 plus G into Z1 plus small q, that is heat supplied per unit mass, it should be equal to U2 plus P2 V2 plus V2 square by 2, that is kinetic energy, plus G into Z2 plus small w shaft, which is the shaft work done per unit mass flow rate of fluid passing through control volume. In this context, capital V indicates velocity of fluid in meters per second. Small v is specific volume of fluid in a meter cube per kg. And let us substitute U1 plus P1 V1 is equal to H1, that is enthalpy of the fluid entering the control volume. U2 plus P2 V2 is equal to H2, enthalpy of fluid leaving the control volume. Substituting these enthalpies in the above equation, we get H1 plus V1 square by 2 plus Z into Z1 plus Q is equal to H2 plus V2 square by 2 plus G into Z2 plus small w. All the energies being in joule per kg. Rearranging the parameters, we get Q minus W is equal to H2 minus H1 plus V2 square minus V1 square by 2 plus G into Z2 minus Z1 joule per kg. It can also be written as Q minus W is equal to delta H plus delta KE plus delta PE, where delta H is equal to change in enthalpy, that is equal to H2 minus H1. Delta KE is equal to change in KE from outlet to inlet, that is V2 square minus V1 square by 2. Delta PE is change in potential energy of fluid, that is G into Z2 minus Z1. All the energies being in joule per kg. This equation, that is Q minus W is equal to delta H plus delta Ke plus delta Pe, is known as steady flow energy equation, abbreviated as SFEE. Very prominent equation of first law of thermodynamics applied to any steady flow open system. Now let us see the applications of steady flow energy equation, that is SFEE, to some steady flow open systems. Number 1. First example what I choose is a nozzle. A nozzle is a steady flow device of varying cross section in which thermal energy of fluid gets transformed into kinetic energy of fluid. Looking at the figure, consider a convergent divergent nozzle where fluid at high pressure, high enthalpy, at very low velocity enters at inlet, that is at section 1. The fluid leaves at section 2 with a high velocity but low enthalpy and low pressure. The fluid expands in a nozzle adiabatically, that is without any heat transfer with the surroundings, and also with no work transfer. W is also 0, Q is also 0. Applying SFEE, Q minus W is equal to delta H plus delta Ke plus delta Pe. Q is 0, W is 0, no change in potential energy, implies minus delta H is equal to plus delta Ke, implies H1 minus H2 is equal to V2 square minus V1 square by 2 joule per kg, that is decrease in enthalpy of fluid from inlet to exit is equal to increase in its kinetic energy. Now considering the example of steam turbine or gas turbine, which are also steady flow open systems. A turbine is a prime mover producing work output. When a high pressure fluid like steam or gas expands in the rotor of the turbine from high pressure to low pressure or high enthalpy to low enthalpy, writing steady flow energy equation, Q minus W is delta H plus delta KE plus delta PE. Many a times steam turbine and as well as gas turbine is an adiabatic device. Steam or gas turbine is an adiabatic device. Change in potential energy is neglected. Change in kinetic energy is also many a times neglected. Then W is equal to minus delta H is equal to decrease in enthalpy of fluid, that is shaft work output by the turbine is equal to H1 minus H2 kilojoule per kg, where H1 and H2 are inlet and exit enthalpies of fluid, which may be steam or a gas. Considering next example of compressor, which is also a steady flow device. A compressor is the steady flow device in which a low pressure fluid is compressed to a high pressure fluid by the shaft work done on the system, which is a negative according to the sign convention of work transfer. Writing the SFEE or steady flow energy equation to the compressor, that is Q minus W is equal to delta H plus delta KE plus delta PE. Compressor, in particular rotary compressor like centrifugal compressor or axial flow compressor, is an adiabatic device. Change in PE or potential energy is neglected, which means minus W is equal to delta H plus delta KE, that is work done on fluid in compressor is equal to increase in enthalpy plus increase in kinetic energy. Next example for steady flow energy equation application is taken as throttling device or a throttling valve or throttle valve. Throttling is an adiabatic expansion of the fluid. Whenever a high pressure fluid passes through a small narrow passage or partially opened valve or multiple orifices, the pressure of the fluid decreases. Whenever a high pressure fluid passes through a narrow passage like a partially opened valve, its pressure decreases from high pressure to low pressure. Essentially, this is an adiabatic process without any external work done. So, throttling can be defined as irreversible adiabatic expansion of a fluid whenever it passes through a narrow passage like partially opened valve or multiple orifices or a porous plug. Applying steady flow energy equation to this throttling process, Q minus W is equal to delta H plus delta KE plus delta PE. This being an adiabatic process, Q is 0. Since there is no external work done, W is 0. There is no change in potential energy because no change in elevation. The velocity of the fluid remains constant, no change in KE, implies the finally delta H would become 0, no change in enthalpy of fluid in throttling process, that is H is constant, that is throttling is an isoenthalpic process. The other effects that we see in throttling are, in every throttling process delta P is less than 0 or negative, since pressure always decreases in throttling. Delta S is always greater than 0, since throttling is irreversible adiabatic process with friction. Delta H is always 0, since enthalpy remains constant as we have proved above. Delta T, as we coming to delta T is also 0 if working fluid is ideal gas. The reason is H is a function of temperature only for ideal gas. That is, H remains constant implies temperature is also constant for ideal gas. That is why Joule-Thomson coefficient defined as dou T by dou P at constant H is 0 for ideal gas or perfect gas. Considering the expansion or throttling of refrigerant in a vapor compression refrigeration cycle that is shown on TS plane, the process 324 is throttling of refrigerant from condenser pressure to evaporator pressure. In this throttling, delta P is less than 0 and also delta T is also less than 0. Both being negative, Joule-Thomson coefficient mu is dou T by dou P at constant enthalpy. It is negative by negative, which becomes positive for refrigerant. The bottom line is the Joule-Thomson coefficient mu value for refrigerant in VCR cycle is positive. Considering next example as the condenser of a steam power plant or thermal power plant, which is a shell and tube heat exchanger. The hot exhaust steam leaving the turbine will enter the condenser, which rejects heat to the cooling water circulated through the bank of tubes, which are shown in the shell. The condensate liquid leaves at the bottom. The hot exhaust stream coming from the turbine is rejecting or transferring heat to the cooling water circulating through the bank of tubes. Thereby the steam condenses into saturated liquid. From the steady flow energy equation, since there is no heat transfer from the condenser outside, no heat losses from the steam to the outside except to the cooling water, the heat lost by steam to cooling water should be equal to the rate of enthalpy increase of cooling water, that is mass flow rate of the steam into enthalpy of the exhaust steam minus enthalpy of condensate liquid should be equal to the mass flow rate of the cooling water. M dot Cw means mass flow rate of the cooling water into specific heat of the cooling water into temperature increase of cooling water. This is the energy balance equation written for the condenser, which is nothing but the application of steady flow energy equation to the condenser of a steam power plant. Having seen the first law in 3 different modules, which is a law of conservation of energy, which also states that energy can neither be created nor destroyed. Now let us look at the second law of thermodynamics, which is also known as law of degradation of energy. Let us start with the second law of thermodynamics, which is also known as law of degradation of energy. Second law of thermodynamics is also known as directional law, because it prescribes the direction in which all the natural or irreversible processes occur. The second law of TD is given in two different forms, even though they are equivalent. That is, violation of one statement automatically leads to the violation of the other. The statement forms are Kelvin-Planck statement of second law of thermodynamics. It states that it is impossible to construct a heat engine operating in a cyclic process which will produce no effect other than transfer of heat from a single thermal reservoir and do equal amount of work. First of all, we should know what is actually a heat engine means. Heat engine. Let us define heat engine. It is a cyclic device which takes in heat or thermal energy and gives out mechanical shaft work. Examples of heat engine are: number 1, steam power plant. Wherein the fuel energy supplied into the boiler furnace releases as heat energy, which in turn is given to the feed water, converting into the high pressure, high temperature steam, which would expand in the steam turbine, producing mechanical work. Number 2, IC engine plant or IC engine power plant. In this, the fuel energy, that is the chemical energy or the calorific value of the fuel given into the engine, releases as heat energy after combustion of the fuel, which gets transformed into the mechanical shaft power output or brake power output of the IC engine, also known as internal combustion engine. Third one is gas turbine power plant. In this heat engine, the fuel added in the combustion chamber of the gas turbine power plant increases the enthalpy of the working fluid, which would expand in the gas turbine, thereby doing mechanical work.